Okay, this should be my last video on our long journey together. We're going to look at specifically how do we use that radio dating or radioactive dating to figure out the age of something. And I decided one of the more difficult problems or concepts to get usually is with the uranium-238. Let's change the color here. The uranium-238 to the lead-206, and how do we use that to determine the age. So I'm going to do a sample problem from the chapter. It's already worked through, but I'm going to kind of explain along the steps. Maybe if they didn't do as good a job, hopefully it'll kind of clarify it. Unfortunately, there's only 3 or 4 problems like this in the back of the book, so you won't get as much practice. That's the other reason I wanted to work through a problem like or from the chapter, so you still had a fair number of sample problems to try. So we have a specific ratio here. The meteor contains 0.556 grams of lead-206 for every 1 gram of uranium-238. So they say assume the meteor contained no lead-206 until the uranium-238 started to decay. And again, we know the half-life for the uranium-238 is 4.5. Oops. My handwriting hasn't gotten any better. It was kind of good maybe a month ago, and then it got bad again. So here we go. 4.5 times 10 to the 9 or 4.5 billion years. So we're going to use that same equation. The ln nt over NO equals negative K times T. And what we're going to do is solve for T. So let's start with that half-life again and the equation for half-life, and we can hopefully find K then from that. And we'll be closer to getting to the solution here. So we have our half-life, again, because it's first order decay. The equation for half-life is right there. So our K should be equal to 0.693 divided by this. And again, our units now are years. So dividing by years, we're going to end up with reciprocal years or per year. And of course, we get a pretty small K here, which makes sense. It is a pretty slow decay or a pretty long half-life. And of course, already not thinking. There we go. Okay, so now what we need to do is figure out our ratio of NT to N0. We know every single atom of lead got converted, or every single atom of uranium-238 that decayed got converted to lead-206. But we just have mass ratios. And remember, we can't compare masses, but we can compare moles. So that's what I'm going to need to do here. Is I'm going to need to take that 556 grams of lead-206, and I'm going to need to divide by the molar mass to find out how many moles of lead-206 it is that we have. So that's how many moles of lead we have, and that means, of course, that eventually originally that was how many moles of uranium-203 we had. So we can convert that back over. We can add that then to the original amount or see how many grams of uranium-238 that is. So we're going to take that value again. But now doing this for the uranium. And we should get 0.6424 grams of uranium-238. So what we can do now is add that to the initial amount. Or so our NT should be, NT should be the 1 gram of uranium remaining, and NT is that 1 gram that we have now plus the amount that decayed over time. So we have the ln of 1 over 1.6424 equals negative 1.54 times 10 to the negative 10 reciprocal years times T time. And that's what we have to solve for, or what we want to find is how much time has passed. So we're going to divide both sides by that. So exact same equation that we used before, we've seen multiple times. Really, again, the big hiccup here is figuring out, what do we do with the lead? How do we find out what that N sub 0 is? And making sure that we're converting the lead over to uranium, unless they already gave us the moles or the ratios of atoms, and then we could just add those together to find N sub 0. It should be, yep, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep. So T here is equal to a ginormical number. You can see we didn't quite decay a half of this amount. If it were 1 over 2, here we go, right here. If that was 1 over 2, we'd know we'd actually be at 1 half-life at 4.5. And we're not quite there, and so our half-life is slightly shorter, the amount of time is slightly shorter than our half-life, which makes sense, which is kind of one of the ways we can check this problem and see if we did it correctly. So that's everything for this. Again, hopefully this video is a little bit helpful. Go in now to the end of the chapter and work, I think it's problems, 55 and 56. Deal specifically with the uranium-238 dating. So if you wanted to practice this again, go in, do those 2 problems there. Otherwise, this is everything I've got. So thanks for a great semester. Good luck on everything. You've all been doing pretty well on the exams and quizzes so far. And enjoy the 2 or 3 weeks you get off after that. Peace.